Hey guys, in this installment here, we're going to be looking at the idea of percent by mass. Okay, so this is really not a super complicated idea, and really all you got to know is the chemical formula, right? So let's say we had nitrogen dioxide, right, which is going to be NO2, and I asked you, so what is the percent by mass? Okay, so there's a little equation you're going to use, percent mass. And all you really want to know is the mass of each individual element divided by the total mass of the compound. So total, let's go here, total mass, okay? So, oh, and then times 100, of course, because you're going to turn it into a percent. So let's go ahead and figure that out. That's pretty easy. So first of all, we need to figure out the total mass of NO2. So what's the total mass of NO2? So we have to do 1 nitrogen and 2 oxygen. So what we have to do is look at our handy-dandy periodic table. We have to say, okay, look, nitrogen weighs 14, right? And oxygen weighs 16. Okay, so I have 16 times 2 is 32, plus 14 is going to give me a total of 46. So I can see that this thing right here is going to have a total molar mass of 46 grams per mole. Okay, so that's my first step. That's going to be my total mass. So I know that that's going to go on the bottom for both of my elements. So now, what is my percentage of nitrogen? Well, my mass of nitrogen here, I only have one of them, so that's going to be 14 grams, right? Because each individual nitrogen weighs 14. So if I go 14 divided by 46, I end up with 0.304. If I multiply that times 100, I'm going to have 30.4% nitrogen. Okay, so that's one answer. Now what about the oxygen? Well, there's a couple ways you could do it. You could just subtract this from 100, knowing that you're dealing with percentages and that's 100, or you could just work it out. And you could say, okay, well, I know that for my oxygen, it's going to weigh a total of 32 grams because there's 2 of them, each having a molar mass of 16. So this was my nitrogen. So my oxygen over here is going to be 32 divided by 46 grams per mole. And so what is that going to be? Well, it is exactly 0.6956 or 0.696, sorry, 0.696 multiplied times 100, and that's going to give me, there you go, 69.6% oxygen, which, like I said, you could have just figured out by subtracting that from 100, knowing it's really 2. But sometimes there's more than 2 elements, and so maybe it's not quite as easy as that until you get down to the last one. But this is how you do percent by mass of any situation. So you just use the masses that you find on the periodic table, divide the mass of the element by the total mass, and you can easily get percent by mass. But there's another concept that comes up in chemistry called empirical and molecular formulas. So first of all, what we want to do is we want to know what in the world these things are. Well, like I just had in that last example, nitrogen dioxide is an empirical formula. How do I know? Well, because this is a formula which shows me my ratio of nitrogen to oxygen atoms, and you can see that my ratio here is 1 to 2, right? So 1 to 2 is my lowest possible ratio. You see, if I had N2O4, that could be reduced down to NO2, right? And so this would not be an empirical formula, although it may possibly be a molecular formula. So a molecular formula is not concerned about having the lowest possible ratio between the 2 elements. And we talk about how in chemistry that ratio is really important. As soon as I do this, nitrogen trioxide, it's nothing like this. And this is a 1 to 3 ratio. So every single compound has a very specific ratio of each atom to the next. And otherwise, it's a different compound. It acts totally different, looks totally different oftentimes. And so that ratio is extremely important. But now in a molecular formula, the ratio doesn't have to be the lowest possible ratio. It can be a multiple, like it could possibly be N2O4. Now, what is a molecular? Well, molecular is what we see in nature. Sometimes things don't assume the lowest possible ratio in nature, and sometimes they'll actually be, a multiple of that. So how do we find that? Well, we have to be given the actual molar mass to find that. So in order to sort of fuller illustrate this, I'm going to go ahead and do a problem for you. So let's say we've got a compound. Here's the compound, and this compound is 5.93% hydrogen. Okay, it's 97.07% oxygen, okay, and it is that's it. And they tell me that the actual molar mass is 34.01 grams per mole. Alrighty, so let's go ahead and figure this out. So how do we figure out the ratio of hydrogen to oxygen? Well, clearly there's a lot of oxygen in this and not a lot of hydrogen. But hydrogen's very, very small, so it's hard to tell really what the ratio is going to be because the masses between this. Oxygen is 16 times larger than hydrogen. So it's difficult to tell. So what do? What we do is we convert to moles. So using that training from understanding what moles are, that's the first thing that we always do. So let's go ahead and convert each one of these to moles. If I have 5.93, what you're going to do is you're going to pretend that this is mass instead of percentage. So I'm going to say, what is the molar mass? So convert from grams or mass to moles. I divide by the molar mass. So the molar mass of hydrogen is actually 1. So this is going to equal 5.93 moles. And I'm going to do the same with this one. So the 97.07, the molar mass of oxygen is 16 grams per mole. So I'm going to divide 97.07 by 16, and I'm going to get 6.06. So this one I get 6.06. And so when you're comparing these two now, you look at this and you say 5.9 to 6.06. It's a little bit off, but it's close enough to say that this is a 1-to-1 ratio. So here's what we have. We have hydrogen and oxygen. So, or probably what we would want to do is we want to say hydroxide. So this is OH, and commonly known in chemistry as hydroxide. But here it is right here. So we have OH. And how do we figure that out? Well, we converted to moles, and then we looked. When we first looked at this, we said 5.9% to 97%. It actually ends up being a 1-to-1 ratio of those two. Because as soon as you convert it to moles, you realize, wow, look at that. They're the same. And so when we convert it to moles, we're putting them along the same playing field. Now, what we have to do is we have to figure out the molecular. So this is an empirical. Obviously, a 1-to-1 ratio is going to be the lowest possible numbers you can have for each one of these. Okay, so a molecular is going to possibly be more than that. So to find out our molecular, first we have to add this up. Well, we know that oxygen weighs 16. And we know that hydrogen weighs 1. So we have a total of 17 here. So if I just have 1 oxygen and 1 hydrogen, my total is 17 grams per mole. It told me that this thing weighs 34. Well, you can clearly see that 17 goes into 34 2 times. So what is the molecular? Well, the molecular is going to be double this, because if I had O2, H2, right, then what's going to happen is I'm going to be able to add 32, right? 32 plus 2, and that's going to give me 34. So the simple way to do molecular is to add up the mass of the empirical, divide it into the molecular, and find out how many times it goes in, and then multiply the whole thing by that. So we multiplied this whole thing by 2 because it went in there 2 times. So we had O2H2, or actually H2O2. Now this helps a lot because H2O2, very different than OH. OH is hydroxide and H2O2 is hydrogen peroxide. So So this is a very, very different molecule than this, and something that's very, very important for us to then know the molecular when it comes into play like that. All right, I'm going to go ahead and do one more example for you on a on an empirical formula. And so we're going to go ahead and use masses right here. So let me find one. Here we go. Let's find one that uses grams. Okay, so let's get a new page here. So let's say that we have something that contains 28.84 grams of sodium. Okay, it has 67.49 grams of chromium. Okay, and it has 72.67 grams of oxygen. So what is the empirical formula? Well, we could look at this and say, well, hey, look, it's this is about 1 to 1, and then this will probably go in there too. So it's 1 to 1 to 2. Well, no, that's not going to work. Because when you look at the periodic table, this is masses. And sodium weighs 23 grams, right? While chromium weighs 52. And oxygen weighs 16. So these things are not comparable just in their masses like that. So we have to turn them into moles. So when we turn them into moles, we're dividing each of them by their own separate molar mass. And so basically it makes them all comparable. So let's go ahead and do that. So this one we're going to divide by its molar mass. So 28.84 divided by the molar mass of sodium is 23. And you can look that up on the periodic table. I'm not going to do that this time. But so look that up, or divide that out. So 28.8 divided by that is 1.25 moles. Okay, so we got that one. Chromium is 52, so we've got 67.49 divided by 52. And that's going to give me 1.297, so I'm going to go 1.30, so 1.30 moles. Okay, and then oxygen, we have 72.67 divided by its molar mass. I'm going to go ahead and put the molar mass here. So this is grams per mole, and this one was 52 grams per mole. You find all these numbers by looking them up on the periodic table. That's how you convert to moles, divide by the molar mass. Remember our little chart that we made back in the mole video. And if you don't know what we're doing here, go back and watch the mole video so you know. 16 grams per mole right here. Go ahead and divide that out, and we get 4.54. 4.54 moles. So what's the ratio we have here? Well, we have 1.25 to 1.3 to 4.54. So now the easiest trick to do here is actually to find the lowest one and divide each of them by the smallest one. And so what that does, if I divide this by 1.25, well, that's going to equal 1. So what I'm going to end up doing is I'm going to end up setting up a ratio, and that's what you want to know. You want to know the ratio of sodium to chromium to oxygen. And then 1.3 divided by 1.5, well, that's going to be close enough to 1. All right, so it's just going to be a little bit off, so we're going to assume that that one's 1 as well. Now, if I do 4.54 divided by 1.25, what do I get? Well, I get 3.6. Okay, so what is that? So basically, my ratio is 1 to 1 to 3.6. Now, 3.6 is kind of troubling because it's not close enough to 4 to round up to 4. And so what is it closest to? It's actually closest to 3.5, right? And so what could I multiply by 3.5 to give a whole number? And so sometimes you have to do this when you're looking at the ratio. So what I'm actually going to do is I'm going to multiply all of these by 2 to get my ratio to turn this into a whole number. So if I multiply 1 by 2, I get 2. When I multiply 1 by 2, I get 2. If I multiply 3.5 by 2, I get 7. And this is actually the ratio that I'm looking for. I got Na2 Cr2O5. Okay, so this is a compound right here. Oop, I put N2. This should be Na2. So this is my answer right here. And so that's a little bit more complex one. So here's what you do. You multiply or you divide it out to turn into moles. And then what you do is you divide each of them by the lowest one. If you get a number like 3.5 or close to 3.5, you're going to want to multiply them all by 2. If you got closer to 3.7, you might want to go ahead and multiply them all by 3 in order to change this to a whole number. If you got 3.3, you'd also multiply by 3. So you got to be careful if you get some decimals in here when you divide them all by the lowest one. But a lot of times in your chemistry stuff, you'll come out with whole numbers across the board. But if you don't, if you come out with a decimal like 3.5, well, then you're going to have to multiply everything by 2 in order to make that a whole number, because you can't have 0.5 of an atom in there. All right, hopefully that helps with really understanding the basics of empirical formulas and how to find out this lowest common ratio between atoms if you're given mass data.